Okay, hello student. We come to the demonstration of some extra example that we going to solve the statically indeterminate rigid frame as shown here. This frame has the fixed support at the C and has the roller support at the A. So if you check this, you may see we will have the reaction over here. Over here, this is going to be C sub x, and this is going to be C sub y. And we also have the moment M sub C here. And for at point A, we have this as the A sub y. And you may see we have four unknown. So our degree of indeterminacy gonna be like 4 minus 3 equation of equilibrium. So we have degree of indeterminacy of 1. And then we are going to solve this by using the consistent deformation. And this problem asks us to use the A sub y to be redundant. Typically, when we select the point or the reaction to be the redundant, we usually to select the support that has only one, okay, redundant, or we select the support that has small amount of reaction. For this one, this has 3, this have 1, so we select, okay, the support, okay, with actually is with small amount of reaction. So we didn't select C sub x or C sub y. That's going to be difficult to solve for the diffraction. Okay, and this beam is what's so called the, no, it should not a steel frame. This one is supposed to be the steel reinforced concrete. Okay, this is the steel reinforced concrete. So it is going to be the RC frame. And what it has the modulus of elasticity of 20 gigapascal and the moment of inertia of 610 power 6. So if you like to see this is in the unit of kilonewton. So this is going to be 10 power 6 kilonewton per square meter. And since we use the square, we use the unit of meter here, this is going to be 610 minus 6 meter power 4. You may do the unit conversion like this. And then, since we have the A sub y as the redundant as specified here, so the first one, that's we gonna start of this after we find as the A sub y, the A sub y is the redundant force. Okay, thus we can consider the frame. Okay, we can consider into two cases based on the principle of superposition. So we can separate the beam or consider this frame. We can the frame into two parts. So let's take this one, and if you can measure this is going to be about 3 centimeters. Let me have this one. So our frame gonna be like this one. This is what this is 3 centimeter. We put this one for 3 centimeter, and we separate the frame into 2 cases. So what are they? What are they? It's going to separate into 2 cases. The one will subjected to the applied force, okay, which we call it the primary frame. So this frame, when you set A sub y as the redundant force, so the statically in the determinate frame, statically in the determinate frame will change to statically determinate frame. Okay, determinate frame. So our frame will change into this, and what we have is the one we will call is primary frame. This one will be called the primary frame. The primary frame is the frame that's subjected to the applied forces. So it's subjected to 10 kilonewton, and also this one 2 kilonewton per meter. So it's important when you select the redundant force. Okay, your frame just change from statically indeterminate to statically determinate, and you use the principle of superposition, separate the beam into 2 cases. One is called the primary frame. Okay, this is subjected to the given loading, and another one is this one that's subjected to the redundant, the A sub y. Okay, this frame is subject to redundant, and then we have this one A, B, C, and A, B, C. Okay, we have separate into 2 cases, and this one is the frame subjected to the redundant force A sub y. Okay, and now we will set what's so called the compatibility condition. So second, okay, we will set for the compatibility condition, and since the A sub y as our redundant, so the compatibility condition at A, okay, we use this, and we can set the compatibility condition by what? Okay, by considering the deformation of the frame. We have, okay, the deformation of the frame. This frame is subjected to this force, and this is the roller, so it may be possible this one will move from A to A palm. And if this one move from A to A palm, this is going to be B palm. So our structure subjected to this uniform force, so it's maybe deformed like this. And since this is going to keep the right angle, so this one will deform corresponding to its support, fixed support here. So the zeta sub c is 0. Also, the delta sub c v and delta sub c h, all of them are 0. So this is fixed. Okay, and what we have now is the deformation here. The delta A vertical is 0. At this point, there is no vertical because there is the redundant force of the A sub y. Anyway, over here, we will have the deformation delta A horizontal, okay, and also this one is going to be delta B horizontal. Since the beam and the frames have the beam and the frames have very small axial deformation, okay, and then you may get this one, delta sub BH will equals to delta sub AH. And also, since there is no shortening or axial deformation of the beam of the column BC, so the delta B phi equal to 0. Okay, and the last one, the rotation. Over here you will have theta sub A. And respond to this, you're going to have the rotation, this one and this one of theta sub B. So that's all the deformation of the frame. That's we know some and some we won't know. What we know is here, that is going to be the geometric boundary condition of the beam. But what we don't know, we can determine later if we like to. Okay, and what else? The primary frame. The primary frame is subjected to this kind of force, and I believe is going to move like this. And since this is the rigid joist, so it's going to keep this one as the right angle, and this is fixed. So this is going to be the deformation of this beam, and you may say that since the A sub Y as the redundant, so we're going to interested in this. What is this? This is going to be the delta at what? At A in the vertical direction for this one. Okay, and also this one, this guy going to deform something like this. If you can imagine it, right? This is going to be the right angle, and what we consider is the deformation in this direction. Okay, that is going to be, we don't know A sub Y, right? Actually, this one is not correct. It's supposed to be here, to be a better one. So it's going to be at the point of A. Okay, this is the delta. Okay, this is more correct than before. And this one going to be what? This one going to be A sub Y, don't know. So usually we will set A sub Y equal to 1 to determine this. This is going to be F. F is the symbol of the deflection due to 1 unit load. And at what? At A. Due to the applied force at A. So this is F sub A. And since this is occur due to 1 unit force, and if A sub Y apply to it, the deflection gonna be this one. So now we are consider the deformation of these frames, this frame, and then we have, this is what? This is gonna be the deformation, the displacement at A in vertical direction. This is also okay, and this is also. So what we have is, this is going to be 0 and equal to, if downward is positive, delta A vertical, and downward is positive is minus F sub AA and then A sub Y. So what we have next is the A sub Y equal to delta, let's say, sub A divided by F sub AA. Okay, this is going to be the compatibility equation at A of this frame. So what next? Based upon this, the redundant can be determined by finding the displacement here, okay, and also the displacement here. That means over here and this one, and then we will use the method of virtual work to determine it, because it's one of the most convenient one. Or if you prefer, you may use the Castigliano theorem to determine it. So the third, just use the third, we determine the force and displacement relationship, okay, which is going to be delta sub AV and F sub AA, and then by using the method of virtual work, the method of virtual work, okay, and based on the method of virtual work, you're going to determine the deflection of this, right? So we have what's so-called the equation of virtual work. So the equation of virtual work, and then it says what? If you like to determine this, the delta, okay, sub AV, you got to what? You got to consider this frame under the application of the force, okay, and then what? You got to put the unit force into this frame in the same direction here. So let's say you got to put 1.0 here. This is 10 kilonewton. This is 2 kilonewton per meter. This deformation here, right? This deformation here is the delta sub AV. This is going to be the delta A vertical. And this one delta A vertical time 1 unit force. And what we have here is external virtual work. Okay, and this external virtual work going to equal to the internal virtual work. Okay, where the internal virtual work come from? Okay, this one unit going to produce the moment, and this moment gonna time something to produce the work, so it's gonna time d theta, and everybody know that from the d square v by dx square equal to m over ei, and you have this one d by dx of what? Of dv by dx, and then this is also m over ei, and you also have this one for d theta, that is going to be m over ei, and this one dx. If you put this is going to be equal to m, and then d theta, that is going to be the internal virtual work, and you do the integration, and since the d theta is here, so it's going to be the integration of m, and then you have m over ei and dx. That is the review of the basis of the virtual work method. Now what you need to determine is what? The M. The M is what? The M come from here, because the M produce the rotation here. So the problem is come to determine the deflection. And next, what we do is we're going to set the coordinate. Okay, so now we set the coordinate. Let's set this is a kind of cantilever frame, right? So we set this one as the x1. Okay, this one from A until B, and also we set this one B until C. This is going to be x2. This is going to determine the M, right? This is going to be determine the M. And then what we have is you can cut this one. Okay, to determine the moment equation. So what actually we need to set, we got to find, okay, 4. We got to determine the equation of M and small m. Okay, and then based on this we do two things. One, we set up the coordinate x1 and x2, and we will use x1 and x2 both determine the big M and small m. And then we also set up the direction of big M and small m. It's going to be the same. If you put this, it's going to have the first portion of this. That is 10 kilonewton, and you have this one for 2 kilonewton per meter, and this is going to for the capital M1. Okay, this is going to be M1. And if you cut this over here, your frame gonna be 3 centimeter, and then putting down a little bit here. And what we have is this is x1, and this is gonna be x2 subjected to the given force 10 kilonewton and 2 kilonewton per meter. Okay, and you set up the direction of this. This is going to be M2. Okay, this is going to be M2. This is going to be M2, if you like. And to determine this, you may do the calculation, summation of the moment over here. If you set this equal to 0, and this is gonna be positive, so what you have is M1 rotate here, and the 10 plus 10 times x1 plus 10 x1 rotate in the same direction, and you get this. This is going to be 2 times x1 and in the same direction, so plus 2 times x1 and times x1 divided by 2, and this is going to be 0. So by doing this, just cut this one, you move this one. That is going to be equal to minus 10 x1, and this one is going to be minus x1 square, x1 square. Okay, that is the first equation for this m1. For this m2, so again, summation of the moment equal to 0. Now, our m2 is here. M2 is here. M2 is going to take here. What we have is this one going to have this kind of moment arm of 3 meters, and it's going to be the same direction. So plus 10 times 3. 10 times 3. And then what we have is this one. It's going to be 2 times 3. And over here, from here to here, is going to be 1.5. So you plus this one of 2 times 3. Of 2 times 3. 2 times 3 is going to be 6. Okay, and times 1.5. And this is going to be equal to 0. And you may have this one, m2 is going to be, this one is 30 minus 30. And this one going to be minus 9. So your m2 is going to be equal to minus 39 kilonewton meter. Okay, this is another one that you can have for this one. Now, if you prefer, you may set this one. Okay, and this one is up to you. This one you may use up downward, because you know clearly this is the downward. Okay, if you put the m1 in this direction, you may get the delta at A is positive. However, if you use this one by setting up A sub y equal to 1, A sub y equal to 1, this one going to be give you the negative. However, you may determine the f sub AA again by using this picture. So it's up to you to determine this. If you like, you may just project this one as you wish before. Just put this one, and let's have the point load here. Let's put it in black of 1.0, and this one gonna be the x1. And when do this, just keep in mind your deflection gonna be just opposite to this. It's going to be negative. It's okay for the convenience of this. So this one gonna be what? This one gonna be m1, small m1. And if you do the summation of the moment here equal to 0, you can see this one going to be really easily to determine of what m1 is going to be x1 equal to x1. Okay, and also for this, just cut it here. It's going to follow the same coordinate. So your frame gonna be cut here, and then you get this as the, just follow this, m2, small m2. Okay, and then this is going to be the same 1.0, and this is going to be 3 meters. And you can see that if you summation of the moment equal to 0, take the moment here, this one and this one is going to be opposite. So this one just get 3. Okay, you are ready now to determine the delta A free. Okay, so this one just substitute into this delta at A vertical equal to what? Equal to integration of this one and this one. Just the integration from where? From this to this, from 0 to 3. Then you get this for minus 10x1 minus x1 square, and then time this one is the x1, and then you dx1 by ei. That is the first portion of this, and then you plus, okay, for the second one, for this one, you integrate it from this to this, integration from 0 to 3, and then you get this for minus 39, and then time this by 3, and then you have dx2 by ei. So that is the integration for you to determine the deltas of AV, and if you do it correctly, you may get this for 461. This is minus, okay, and this is minus. You will get this for the minus 461.25 over ei. This negative because the direction that you use is opposite to what it should be. Okay, so if you like to answer it clearer, just put this one equal to 461.25 over ei, and direction just opposite to this is going to be downward. So keep this in mind, and we will use this later. Next, now we have this already. Next, f sub aa. Okay, the equation of virtual work going to be 1.0. 1.0. 1.0 is what? 1.0 is the force that's acts on this frame. Okay, if you put this one in this direction, that is going to be 1.0. 1.0 going to time f sub a. Okay, we set a sub y equal to 1. And then that is external virtual work. And this one going to produce the m. This one going to produce small m. Okay, that is going to be small m. And since this one has the deformation this way and sets a sub y equal to 1, so this m is going to be this m. So that is going to be m square integration. Okay, and then you have the dx over ei. That means you got to determine what? You got to determine the moment, okay, of this one, x1, and also the moment of this one. For what we have is the x2, and then we have this already, right? So we have f sub aa equal to the first one, integration from 0 to 3, so x1 square, and then dx1 over ei. And the other one is here, plus 0 to 3. This is going to be 3 square, and dx2 over ei. Okay, this is going to be 9 times 3, 27 for sure. This is going to be x power 3 divided by 3, and it's going to be 9. Okay, so 9 plus 27, this is going to be equal to 36 over ei, and this one is upward. Okay, now we can determine the delta sub AV and F sub AA, and the sixth step, we're going to find the A sub Y and the reactions of the frame. Okay, by doing this, your A sub Y is going to be equal to 461.25 over EI, and then it's going to divide by 36 over EI, and EI cut EI, you get the A sub Y, right, of what? 12.81 kilonewton. So this one gonna be 12.81 kilonewton. That is going to be the reaction that we are looking for it. So this is the important answer. From this, now we can start to find the reaction. If you like to define the reaction, come back into this one. Okay, you're going to determine the reaction for this. Just put this one is 3. I mean the reaction here, okay, 3. And you also have this one for 3. And your frame subjected to at a 10 kilonewton. And this one is 2 kilonewton per meter, and you have the reaction. Let's say this one gonna be C sub X, and under the force here, I forgot, this is gonna be 12.81 kilonewton. So this one is up, down. So we should has this C sub Y here, and also we should have the moment here of M sub C. Now, if you like to do so, you do the summation of X sub X equal to 0, and since it's nothing, so your C sub X gonna be 0. So C sub X is 0. And if you do the summation of F sub Y equal to 0, upward is positive. Your C sub Y is upward. Okay, this one is downward of 2 times 3. This one is 10. So this is going to be upward, plus 12.81 minus 10 minus 6 equal to 0. If you put this into your equation, your C sub Y gonna be 16 minus 12.81. Okay, so C sub Y is gonna be 3.19 kilonewton. And the last one, summation of the moment at C equal to 0. Now you have your M sub C, right? Your M sub C gonna be in this direction, so you put this one as the positive, and then you got to move your M sub C a little bit this way. So your M sub C is what? Your M sub C is clockwise, so M sub C is clockwise. And this one also produce the clockwise direction. This one gonna have time 3, so plus 12.81 times 3. And 10 is opposite direction, minus 10 times 3. And this one has direction here, minus 6 times only this time 1.5. And then this is going to be equal to 0. Now you can do the computation and you will get m sub c of 0.57 kilonewton meter. Okay, that is the reaction of overflow. Now, next thing, we're going to draw the shear diagram and moment diagram of the frame. And the frame can have the beam AB and the column AC. So let me put this one here. 3 centimeter from this one A and this one B. And we also have the column. That is going to be B and C. And for this, the shear diagram and moment diagram supposed to be here. And also this one supposed to be in this direction. And what we have is the force, that is 10 kilonewton. And this is going to be 2 kilonewton per meter. And this one is going to be 12.81 kilonewton. And for this one, no forces. And we have this one for 3.19. And also we have the moment here of 0.57 kilonewton meter. Okay, we're going to determine the end moment and end shear here. And if you prefer, in this case you don't need to, because there is no applied force at this point, so you can transfer from the beam to the column directly. But I like to show you to make everything clear up, right? Okay, this one, doing this one gonna be the V sub B. It's supposed to be 10 and 6, so it's gonna be this one. And then if you do the summation of f sub y equal to 0, you may have this one for your V sub B. Your V sub B is up, right? It's up. So the V sub B is up plus 12.81. Actually, you don't need to, but it's okay. It's going to be the same thing. This one plus this one, 12.81, and you're going to be minus 10 minus 2 times 3, and then equal to 0. And then you will get your V sub B equal to 3.19 kilonewton. And this one going to be downward here, and it's going to be upward here, and it's going to be downward here. So this one is 3.19. This one also 3.19 kilonewton. Okay. And since this one is 0.57, you can see that this one also, if you take moment here, summation of the moment equal to 0 here. So you m sub b equal to this one, 0.57 kilonewton meter. And if this one is 0.57, this one also, and this one also, and this one also 0.57 kilonewton. meter. Okay, that is ready for you to draw the shear diagram. Set this one as the x meter and this one for 3 kilonewton. And this one is 0. This one is 3 meter. And then you have this one 10, this one 12.81. So 12.81 is larger. Just push this one about 2.81 millimeter. So we set 1 millimeter equal to 1 kilonewton. And then you got this for plus 2.81. And this one is 2. Okay, so your dv by dx equal to slope equal to minus 2. Okay, and you also know that this is going to be 3.19 up. Actually, it's going to be something like this. And this is going to be minus 3.19. If you know that. If not, you can prove it. Okay, you may prove this one by what? By v sub b minus v sub a minus 2.81, and it's going to be equal to minus of the area here. That is equal to minus of 2 times 3. So your v sub b is going to be minus 6 plus 2.81. So the answer is going to be equal to minus 3.19 kilonewton. Okay, you may prove this. And then your curve is going to be something like this. And it's close here. And this one going to have 0 kilonewton shear. Okay, and you should put this one for markup of the slope. And if you like, next we do the moment diagram. This one again, x meter. And this one is the roller, has no external moment, so this one is 0. And then we set this is moment kilonewton meter. Okay, this is start by 0 kilonewton meter. And then when you come here, you're going to have the slope here. And it's going to be dm by dx equal to 2.81. And then the slope gonna be changed. The dm by dx gonna be 0 here. And what is this? By the similar triangle, 2.81 divided by x equal to 2. So your x is going to be 2.81 divided by 2. And your x is going to be 1.405. So this is 1.405 meter. Now, you don't know the moment here, right? Yes, you know that. So the moment here, the moment here, minus 0 is going to be equal to the area here, 1/2 of 1.405 and times this 2.81. Okay, and then you will have the moment of this 1.974 kilonewton meter. Okay, okay, and then you may set like 2 centimeter. You have only 1 centimeter. So this is going to be 2 kilonewton meter, 2 kilonewton meter per 10 millimeter, something like that. Okay, that is about very close to. Okay, this is going to be the dm by dx equal to 0, and then you point this one out here, very clear, and the curve gonna be something like this. And if you like, just highlight this, and then highlight this. Okay, and then what we have is the shear is going to be reduced, and until here the shear is minus 3.19. So this one dm by dx gonna be minus 3.19. Okay, and the moment here is what? Is going to be this. You may check this one, moment, and this one going to the same direction. This one plus 0.57 equal to 0. So it's going to be minus 0.57. Then the curve going to be down, back, and here. Okay, and what we have is this one is the point of 0 moment, and it's going to be the inflection point, right? It's going to be the inflection point. And you may prove, if you don't know this, we may say m sub b here, minus here, minus 1.974, and then it's going to equal to the area here. And since this one is 1.405, this one is 3 minus 1.405 is going to be 1.595 meter. Minus 1.595. And then, oh sorry, this is 1/2 of this, and minus 3.19. Minus 3.19. Okay, you may have this one is negative, and this one is positive. And you may have, if you do the computation, m sub b equal to minus 2.544, minus 2.544, and then plus 1.974, and this one is going to be minus 0.57 kilonewton meter. Okay, you may clear up this like here. Next, we do the shear diagram, moment diagram of the column. And again, you may start by putting this one. And do we have shear here? We have no shear here. And this is x, and then meter. And then you put this one of the 3 kilonewton. And since there is no shear, so this is going to be 0. And the dv by dx, w equal to 0, and all are 0. Okay, and for the moment, again, this one going to be x meter, and this one is going to be m kilonewton meter. And what we have is this one sign convention of m, and this one in opposite. So our moment is going to be positive. Sure, since this one is the clockwise moment. So it's going to be 3.19. No, it's going to be up. Plus 3.19. And since the shear is 0, so dm by dx is 0. It's going to be constant. And it's close here with 0.57. Okay, that is going to be the moment diagram of this. And if you like, you may also draw the N diagram. Okay, the normal force diagram. And this is what? The compression. So you may set this one as the N kilonewton. And since it's compression, oh, sorry, this is wrong. This is going to be what? 0.57. And this is close by 0.57. And this one is compression, minus 3.19. And it's also, you can cut it anyway. It's going to be minus 3.19 until here, close. This is x meter. This is minus 3.19. This is called the normal force diagram. This one is the M diagram. And this one is the shear diagram, if you like. Okay, that is all for what we have. The shear diagram and moment diagram of the beam. And this one is shear diagram and moment diagram of the column. And then for the elastic curve, draw the shear and moment diagram of the frame. Okay, and then 6, we will draw the elastic curve. Okay, next we will draw the elastic curve. What we have is we have the frame of 3 meters here and 3 meters here, and this is fixed, this is the roller, and then this is on the support we have. Okay, as we mentioned before, the delta sub ch equal to delta sub cv, and this is zeta sub c. All of them equal to 0, no movement. Under application of this one, the frame may move here, and what we have is this is going to be positive, and it's going to curve like this, and this was negative. Okay, it's going to curve like this. So this one may have the curve like this, and it's going to return back. Okay, this is going to be returned back like this, and it's going to keep the light angle here. Okay, and this one, you may see this is negative, right? This is negative, so this one gonna curve like this for negative moment. And then what we have is this one gonna curve and have the compatibility, and have the boundary condition here. And this is going to be the point of, this is going to be A palm, from A to A palm, and from B to B palm. And what else is going to be the same as before? And this is going to be what? This is going to be the inflection point. That is the point that moment change from plus to minus or minus to plus. And when you put the reinforcement, the reinforcement is going to change at this point also. Okay, and what else? This is going to be what we have mentioned, delta AH, and this is delta BH, and they are going to be equal. Okay, next. We put the reinforcement into this. Okay, and as I mentioned before, the reinforcement may be for the main reinforcement. Put this one like this. Okay, and what we have is for this one, we're gonna put more reinforcement up into the inflection point. And again, for this one, we put it on the top of for the negative moment on the top. And since this one is going to have the tension, so this is going to kind of extra reinforcement. So this is going to be the reinforcement pattern. Okay, this one going to be the elastic curve. Okay, that's supposed to be all we have for this example. Let we go back to check what we have. We start this problem by considering this frame that's going to have the degree of indeterminacy of equal to 1 by checking the degree of indeterminacy for unknown reactions with respect to the number of equation of equilibrium. So we have 1 degree of indeterminacy. And since we have the consistent deformation method, in which this consistent deformation method is a kind of what's so-called force method. Force method of structural analysis. That means we're going to use force equal to the redundant. Okay, so typically anyone can be the redundant, but the one that isolate from the author, okay, is going to be selected. In this one, it's really convenient to select the A sub y as the redundant, and the problem set us like that. And then they ask us to determine the reaction. After we find the redundant, we can then later to determine the reaction. Okay, it is here. And when we select A sub y as redundant, the frame will change from statically indeterminate to statically determinate. So we can consider the deformation of the beam, so the frame, and then we set up the compatibility at A. Okay, A sub y as A. The deformation of this one is like this, of this one is like this, and this one is like this. And at the point of A is 0 here, is equal to the downward delta sub AB and minus F sub A sub Y. You got this equation is the compatibility condition And if you can determine the force relationship of these two displacement, you can get the A sub y. And you have two methods to analyze the frame. One is the method of virtual work, and another one is the Castigliano theorem. It's better to use the method of virtual work. And then you set up what? The equation of virtual work. Okay, you set up the equation of virtual work. And the external virtual work is equal to the internal virtual work. That means you're going to determine the delta sub AV. That means you're going to put 1 unit force at point what? Delta A at point A in the vertical direction. Okay. So this is going to produce the capital M. This is going to produce small m. For the capital M, you go here. Okay. And for the small m, you may use this one in the opposite direction of this. And you keep in mind that the deflection delta sub AV that you get will be negative because you set this 1 point unit load of A sub y in opposite to this. So don't worry, just do the same. You use your basic from engine static or the basic from what you have from the previous knowledge. You can find the equation of the moment m, capital M, and the small m. By doing so, you do the integration, you get the delta sub AV. And again, for this one, the deflection is over here. So it's really convenient in this way to set both m equal, because the A sub y cannot use. You got to set A sub y equal to 1. So this figure and this figure, they are the same. And they are the same pool. Then this equation will be m squared. And you have this. Finally, you got the A sub y here. From A sub y here, you put the A sub y over here. And then you can determine the reaction. After you determine the reaction, now you can draw the shear diagram, moment diagram, draw elastic curve, putting the reinforcement as you use the moment diagram and the basis of this. Okay, that's all we have for this problem. You guys supposed to try to work on this by your own, and if you cross everything and you work as you watch my video clips and you do very good calculation, that's really nice. That means you have some skill to solve this problem. Okay, that is the end of the clip.